It's that time of week again, Sunday, 6 p.m. Pacific. Welcome to Steve's Place. Tonight we're going to have a super interesting guest, Randall Carlson. He's an expert on sacred geometry, and I think we're going to find his presentation quite interesting. But before we get to that, I want to remind people to sign up for our YouTube channel. Uh, it's uh, we have over 1,500 videos up there. I encourage everyone to become a become a member. It's $9.99 a month. Gives you global access 24/7. Anywhere you can get YouTube in the world, you can access our YouTube channel. We have a free subscription, which has a couple hundred videos. But for the most part, we really want you to encourage you to all become members. It really helps us out. And then I also want to talk a little bit about our conference coming up August 7th and 11th. That's just a couple weeks away. And I encourage everyone to come there for the in-person experience. We still have hotel rooms, for like $84 up. Includes breakfast. If you have a problem getting that rate, you give me a call and we can get it worked out with the hotel. They're supposed to be keeping that rate until July 30th, okay? And when we start off, we'll be kicking off with, well, we'll be ending up with John Peterson and Greg Braden on Saturday. We don't want you guys to miss that. Be telling you what's up and what's in store for the future of the world here. And if you notice in the corner there, we have a little QR code. We're doing a live stream this year, and if you click on the QR, it will take you to the sign up page, and it'll be $99 a month. I mean, not a month, $99 for the live feed, and we'll be talking a little bit more about that with the producer Mike at the end here of the show. So, without further ado, let me introduce the star of the show here, Randall Carlson. Welcome aboard, Randall.
Well, thanks for having me, Steve. I know you've been trying to track me down for years and years, and I finally gave up and said, okay, I'm going to be on the TeslaTech show with Steve. So I'm just, in fact, I'm just kidding. You know that, Steve.
So, anyway, tell us a little bit about yourself.
Well, during the daytime, for most of my adult life, I've been a professional builder. I mostly build houses, but I build some other things too, restaurants and retail spaces, things like that. But mostly residential structures, and we do the design build. And my dad was a carpenter, and his dad was a carpenter, and we started out, me and my brothers as teenagers, learning to build houses, and I just kind of fell into it. Didn't intend to. It just was while I was going to figure out what to do with my life. I decided I would. I learned a few carpentry skills, so I picked up some carpentry work, and then I discovered, you know what? I really like being my own boss. I like working outside, and I also like the challenge of figuring out how to build things because a lot of the early things we built, this was back in the early '70s, and remember, Steve, what geodesic domes were? Do you remember those Buckminster Fuller domes?
I remember them.
Yeah. Well, a lot of people were building them back then, and we got a couple of jobs, my brothers and I, building a couple of those, and I found that geodetic geometry very intriguing, and that kind of led me into, wanting to learn geometry. And then one of the domes that we built up in the North Woods of Minnesota was especially designed. It was called a Bindu dome, and it was kind of based on the geometry of a Islamic mosque with a spire on top. And so having to figure out how to build those, cut the struts, and do the geometry and all of that just really kind of fired up my interest in geometry. And then that particular dome was published was featured in a national publication called Shelter, and that was sort of a book about how different cultures around the world and through history used the built environment, used building and architecture to interface with the environment in various ways. And in there, I learned about something for the very first time. This was 1973, called the golden section. And I thought, this is really interesting stuff. And so, using that as a kind of a lead, I found a few other things. There wasn't a whole lot available on this topic in the early 70s, but I tracked it down. And, by over a few years, I'd started assembling a collection of materials together on the subject and realized, boy, there's a lot to this. When those guys were building those mosques, when they were building those cathedrals, these guys were some master geometricians to do this. And then I began to appreciate and realize when I studied the dimensions and the proportions of an ogival vault in a Gothic cathedral, realizing, well, those carpenters had to be really top notch, because this is some really sophisticated geometry that they're using here to build the formwork. So that's where kind of it started, and I've kept up my interest. I started in the early 80s. I was neighbors with an architect, and he knew I was studying this stuff, and he got a bunch of his architect friends over, and I gave a presentation to them. And I think that was the first time I ever gave I went in, I did a slideshow I put together. There was no such thing as PowerPoint or internet or all that back, 1980, whenever it was. And I found it was received well. I had a lot of fun doing it. And then I think through references, I got requested to present a few other places, and then it just went from there. It became a hobby, and I've continued with it to this day, studying and learning. And there's always more stuff to learn. And now with the internet, there's a lot of information out there that certainly wasn't there 25, 30 years ago. That you had to do some serious digging, actually, like get up physically and go to a library and look stuff up. So that's kind of where it's at. What I've done now is my other interest in life is geology and earth change. So I've done a lot of, let's see, I'm just getting a message. I should turn up my volume. How's my volume, Steve?
It sounds okay to me.
Sounds okay to me. Let's see here. On Scarlet. Oh, right here. Okay. Well, it's pretty much up all the way on the Scarlet.
Yeah, I could hear you okay.
Okay, well, if you can hear me, we should be good. I guess my brother might have been listening, and the volume sounded low. But yeah, if it sounds okay to you, it's probably sounding okay to anybody else who's listening. So, but that's the gist of the story there. And I'm kind of semi-retired from the building business. I'm just reserving now for very special projects. My team isn't the level that it was now. My brother is the project manager. We're doing a project right now, and it's small compared to what we used to do. But we're still hopefully going to be doing more building, except very special projects. In fact, projects that may include the principles here that we're going to be talking about in a few minutes, the sacred geometry and so on. Because one of the things I'll tell you, Steve, I'm very interested in doing is recovering as much of the ancient system as I possibly can, and maybe recasting it using modern technologies and so on. I mean, I'll give a quick example, and then we can get into the specifics. Now, I mean, in the old days, if you were going to lay out a circle, which is where usually most all construction began, whether it was even a square building, it began with drawing a circle. Okay, if you draw that circle, it starts with putting some type of a pole or something in the ground vertically, right? And then you would hook like a knotted rope or a linked chain. Linked chains were great because if your links were uniform, those were your units of measurement, so you could count and know exactly what your diameter was. But in any case, you simply draw a circle around there. Okay, that would be the same operation that you could do, let's say, on a piece of paper, on a drawing pad or something, using a compass and a straight edge, a set of compasses and a straight edge. And so now, if I was going to do that and replicate the process of laying out a circle and then transposing some geometry onto it, I'm probably not going to use a knotted rope in 2024. I'm going to use a laser transit, right? So we can take the ancient principles and we can adapt them to modern technologies, absolutely. So that's where I'm interested in going with this as far as, in the future, which hopefully isn't too far in the future. And I know I've already talked to a few people about the potential of using some of the principles of sacred geometry in creating spaces, houses for people to live in. And I think without getting into any of that tonight, because we don't have time, this is what I get into, and when we do courses and workshops and things like that, is what we're looking at space and spatial relationships in geometry. But there's another factor too, is because that the ratios, for example, the square root of 2, the square root of 3, the square root of 5 to 1, those numbers also represent vibrational frequencies. And so now we get into geometry not only of space, but the geometry of frequency, which is basically the geometry of time. And it gets pretty sophisticated there. And I still have a lot to learn because there's always new stuff being discovered. But I put together a little exercise here for us tonight to go through, just to give people a taste of some of the linkages and interconnections, some of the subtleties of the system of sacred geometry. So should we just dive right into it?
Sure, let's just go ahead and dive into it. Now,
all right. So I will hit my present button here, share screen. Let's see here. Okay, now it should give me an option. Which screen? Let's see. We did this. Okay, here we go. Select a window. Screen. I think we're going to try screen 3. Let me allow and see what happens. All right. Are we seeing? Okay, that is not exactly what I wanted to see. So let me just see if I can. Actually, I wanted screen 2. Sorry. Let's stop screen. And then I'm going to screen again. And I'm going to share screen 3. That's what I wanted to do. Select window or screen. There we go. Allow. Did it default to the same screen?
yeah, it went right back.
You're seeing thumbnails, right?
Yes.
Okay. Well, why is it going back there? Okay, we'll get this. I'm going to stop sharing. This one should get it. We had it last night, no problem. Share screen. Okay, share screen. Screen 2. Okay, now we're good. Sacred geometry, the hidden patterns of creation. Yep, there we go. Okay, so this is a very simple rectangle. It's a double square, and I'm not going to show how we would lay that out or draw it. It's just one of the very simplest of geometric exercises. But many of the exercises that we do, almost all the drawings, no matter how complicated, how complex, all of these developments, the graphic developments of sacred geometry, begin with a circle and a square. First thing is the circle. You lay that out, and then once you've got a circle, through a series of geometric steps, you can create a square. And then once you've got a square, it's very simple. I'm going to use my cursor here, and you can see there's a square. Now, typically in classical geometry, you're using the circle, and you're using the compass with which you draw circles and arcs, and you use the straight edge, which you obviously draw straight lines because you want to connect points. So, for example, if I have a square here and I want to have a double square, which is a 2-to-1 rectangle, I simply use my straight edge and extend that side on out, and I would use my compass to step off unity, which would be the side of my square. Now, you'll see here when we come up and I show you a circle in a minute, an inscribed circle. So what you're essentially starting with is a circle, and then you draw a square around that circle where the sides of the circle are the circumference of the circle is tangent to the 4 sides of the square, and then obviously the diameter of the circle is going to be the same as the side of the square. and we're going to call that unity. Now, we could use the radius of unity, or we could use the diameter. It doesn't matter, because when we start talking about proportions, it doesn't matter what your base unit is. It's going to all reduce down to the same proportions. So we're going to start with this double square, and then we'll find that there's many uses, many places that the double square has shown up in history, in architecture, in art, and so on. And here, of course, is one of the more well-known incarnations of the double square, is the King's Chamber of the Great Pyramid. And it's based upon a double square, which is 20 cubits by 10 cubits. Okay, so we'll take that geometry and we'll just work with it a little bit here. And we draw in the diagonal, and a simple application of the Pythagorean theorem will give us the length of the diagonal. So we simply square the short leg, we square the long leg. So we get 2 squared is 4, 1 squared is 1, 4 plus 1 is 5, and then that will give us the square root of that will give us the diagonal. Okay, so now a couple of simple steps here that we can do to take this geometry and develop what's called the golden section, which is simply a continuous proportional relationship where you have a line length, like I'm showing here. You have a short segment and a long segment. It has to be asymmetrical. And what you're interested in here, with this particular golden section of a line, is finding that point where the ratio of the small to the large is the same as the large to the whole line, the sum of the two. Or you could go conversely. What is the ratio of the whole line to the long segment? And that's going to be the same as the long segment to the short segment. You set it up algebraically like this: A over B equals B over A plus B. So then you can solve this using the quadratic formula, or the completing the square system. I think there's like multiple different ways you can solve this. And what you end up with is an irrational number that never repeats, never terminates. And this is the so-called golden section, golden proportion, divine proportion. I think was pretty well known in the Middle Ages, and then recovered a lot and discussed during Renaissance periods, then kind of forgotten about, until the early part of the 20th century, really to the mid part of the 20th century. And then, like I said earlier in my introduction words, that, I discovered it in 1973 because they had a page devoted to it in this book, Shelter, and some of its applications and so on. But this is supposed to be, philosophically, the idea was that this was the basic proportion of harmony. That what happened was, when you utilize this proportion, whether it was art or architecture, you were in effect mimicking nature, because nature utilizes this ratio in order, particularly in growth processes. You see it in botany, you see it in, for example, the spiral of a nautilus shell. You can see it actually in astronomical examples, and I'm going to show you one prominent example here in this talk here coming up, and you'll see it for yourself. Anyways, this is the basic formula. When you solve it, you get this value: 1.618033989 ... going on forever. Never terminates, never repeats. But the way to get that number, if you're trying to get it in your calculator, is interestingly, because 1 plus the square root of 5 divided by 2 will give you that number, 1.618033989, et cetera, which is also the number you get when you go to the Fibonacci sequence. And the Fibonacci sequence is just a sequence of numbers wherein each value in that sequence is the sum of the two preceding values. And you can see that here. 0 plus 1 is 1. 1 plus 1 is 2. 1 plus 2 is 3. 2 plus 3 is 5. And in this sequence goes. Now, when you set this up in a series of successive ratios like this, you see this, 1 to 2, 2 to 3, 3 to 5, 5 to 8, 8 to 13, et cetera, et cetera. What happens is you'll discover, and we're not going to do this for the sake of time, but if you have, one of these, a calculator, you can play with this yourself. You may know some of this already, but anyways, if you take the successive values of each ratio, what you find out is that the golden number is the limit of that process, right? So what happens is that you'll find if you plot these values on a graph and your golden numbers is 1.618033989 dot 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 to indicate that you know that it goes on forever and never terminates and never repeats, what you'll find then is that each of the successive fractional values here will converge on that as a limit. And of course, it never does actually reach the limit until your successive values get infinitely large. But what happens is it alternates above and below, above and below. And as you go through these numbers, as you go through and plot the ratios, and it's a fun little exercise, and I would recommend trying it if you want, and you'll see that it alternates. It'll go above the number, it'll go below the number, it'll go back up above the number with the next pair, then below, then above, then below. And each time it's coming closer and closer to that golden number as the limit, which is the 1.618. So this is the Fibonacci sequence right here. And you can see, 55 plus 89 is 144, and you can keep going. And the larger the numbers, of course, you're going to find out, the more data points you have in your formula, the closer it's going to get to the magic number, which is the golden proportion, the golden section, the divine, whatever you want to call it, right? It's been called a bunch of stuff. Okay. So here, back to what I've done here now is I've taken the triangle that is based upon where its hypotenuse is the diagonal of the double square. So we've got 1 square root of 2 and, 1, 2, the square root of 5. So what we're interested is now you can see that the values that we want to get that number are all here. We've got 1, we've got 2, we've got the square root of 5. Now we can prove that, there's an algebraic proof for this, which I'm not going to do tonight. In my courses and classes, we do work through that because it's a lot of fun to do an algebraic derivation, but it works out to this. If you take if you're at home, you got a calculator, grab it, put in the square root of 5 plus 1. So you're going to get square root of 5 is about 2.236067978, I believe. Doesn't matter. Square root of 5, add 1 to it, you're going to get 3.236, etc. Then divide that by 2. And what you're going to discover, 1.618033989. So there it is. So let's look at here. We got so the first thing I am going to do is I draw a circle on the upper vertex of the right triangle here. And that circle is going to have a radius of 1. We'll call the radius 1. That'll be unity, and everything will then build from there. So if the radius is 1, this is a double square, it's going to be 2. And we just showed that the hypotenuse, which is the diagonal of the double square, is going to be the square root of 5. So you'll notice then that I've taken the square root of 5 and I've cut it at this point where it now divides that diagonal, where you've got square root of 5. This is 1. Then you've got this longer section here, which would be the square root of 5 minus 1, okay? And then if I were to extend this out, look what you get. Square root of 5 plus 1, right? And then this is 2. So now I'll go to the next step of this exercise, and I'm not going to work through all the math on this just for the sake of time. But now I have a circle whose radius is the square root of 5 minus 1. I've drawn that circle on the other vertex, and it intersects my baseline too at this point right here, right? Well, guess what I've done? It just turns out that I have divided the baseline 2 in the golden ratio. So there it is. That's how simple it is, you see. And so you can come at it two ways. Remember I showed you can go the smallest to the largest to the whole, or you can flip it and you can say the whole line is to the large segment as the large segment is to the small segment. So you can come at it both ways. The equation that you would solve would be square root of 5 plus 1 divided by 2, or the square root of 5 minus 1 divided by 2. Okay? And you can extrapolate both of those out of this diagram right here. So that's a simple and easy, quick way. And of course, you don't need to even draw the whole triangle, do you? If you're just looking to divide a line, it's also called, I will say, the division of a line into mean and extreme ratio. Le Corbusier, famous Swiss architect, first half of the 20th century, developed a whole system of architectural proportioning using this particular ratio of small to large and large to whole, and it's expressed here. One of the interesting things about this is that this particular ratio is the governing mathematical ratio of human anatomy, and we all kind of revolve around that golden number. Some of us hit right on, some of us don't. But it's interesting, just like with the Fibonacci sequence, the more data points you have in your ratio, the closer it gets. If you start measuring people, what you'll quickly discover is that after you get a couple of dozen people in your database of accurately measuring, is that the navel divides the height of the human body at that golden section point. Some of us may have short legs, some of us may have long legs, some of us may hit on it, right on it. But the idea is that when you start measuring a whole lot of people and you're averaging them, you then will zero in on the golden section as a limit. So Corbusier developed a whole system around this that he called the modular system, and he's showing it here. These arcs are simply would be pieces of a circle, that if you go back to here, those arcs would be, an arc on the short side, an arc on the long side, arc on the whole, and that's how he developed this spiral form here. You can see it's expressed here as well in this diagrammatic form. So he built a whole system of architecture around this. And this is just my hand, and anybody's hand. It'll show you the just one way that this is built into the human anatomy. You can see here that the division of the knuckles shows a golden section sequence. So here you've got A to AB is the short section, BC is the long. If you add them together, you get to C and D. But CD is to be CB as CB is to BA. You get that? Or you go the other way. AB is to BC as BC is to CD, as CD is to E. Hope you followed that. And so obviously people have different shaped hands. Some have larger, some have smaller, some have longer fingers, some have shorter fingers. Again, the key is that some people's hands might hit right on it. Actually, it turns out that my hand is pretty much very, very close with as precision measuring as I could of the actual joint there, the knuckle. Interesting, you could go beyond this. Like if you are sitting here, wherever you are and you're listening, do this. Take your forearm, your elbow to fingertip, right? Now, think of that as a cubit, and you're going to divide that cubit into golden section. It turns out that right down at the wrist joint, you'll feel it. If you're holding if you're probing with your finger, you're going to find a space right here in your wrist joint called the space of Destot or Destot. And that is what I'm marking on my diagram that you see, right here is that space. And if you take your whole cubit, what you'll discover is that space, which defines your wrist joint, divides your cubit like into the golden section. You see that? Okay. So now what I've done here is I've taken that square and it's got an inscribed circle. You can see that the circle has the diameter equal to the side of the square. And what I've done is I've just done projection lines off the square and the division of the square, right? See, I've got through the middle, I've got a horizontal axis and a vertical axis. I'm just projecting that vertical axis right on out 1 unit. I'm projecting the side out 1 unit to add this additional square, to append this square to this smaller square that's 1/4 the size of my original square here, okay? Now I could have done that anywhere around 8 different places, right? I'm just, for ease of demonstration, I'm just going to go up on the left side. So now you can see in this, I've got plenty of, I mean, let's count. How many double squares do I have here? Quite a few, you know. I mean, I could count 8 of them easily. And here's this one that I've generated by projecting this side square. So I've got a double square right here. So let's just go through. Let's see, where am I here? Square combined. Yeah, there we go. So here we go. Here's the exercise. Okay. Then I'm going to add another circle up there. I'm using this corner of the square as the center of this circle. Okay. Now you can see what I've got here. I built in, by adding this circle, this is what, in a sense, what I did on the exercise where I showed you I juxtaposed the circle onto the vertices of the triangle. So right in here, you can see if I were to draw a diagonal here, it's going to be cut right there, and that'll give me the square root of 5 minus 1. Or if I project that on out to here, it'll give me square root of 5 plus 1. Right there. See what I did? Now, there's nothing arbitrary here. Every step of this operation requires the previous step, right? Each step generates the following step. So now what I'm going to do is, remember, square root of 5 plus 1, divide by 2, right? That's one of our equations. So I'm going to divide this line right here in half. And that half point is going to hit right in here. Now, how do I get that? Well, it's very, very simple. I just use a compass open to greater than half, and I swing arcs from both endpoints of the line, and then the intersection of those two arcs is going to give me the midpoint. And again, in a geometry workshop or course or class, we go through this whole process step by step, and I'm a firm believer that as many of your senses that you can engage. In this case, when I do a sacred geometry course, I want people to think. I want mind, hand, and eye to all be coordinated. And that's one of the interesting things, is when you do geometric exercises, drawing exercises, does engage the mind, the eye, and the hand. And so in the courses that we do, I provide custom-made compasses for all the students or participants, so that it's a course in drawing. That's what it is, geometric drawing, because there's no better way to learn the system than making these drawings. Okay, so now we're going to divide this in 2. There's square root of 5 plus 1, and now we're going to divide it in 2. You can see there's a dot right there. I've gone ahead and done this because I'm skipping steps here for the sake of time. But now I have the square root of 5 plus 1 divide by 2, so this should be my golden number right here. Add it up. Again, if you have a calculator handy, grab your calculator, put in the square root of 5, you'll get 2.236, etc. Add 1, you get 3.236, etc. Divide that by 2, you're going to get 1.618, etc. So that length should be in there now, assuming that our original circle, that the radius was 1, right? That was unity. That was our unit circle. So now the square is 2 units on a side. The original inscribed circle is 2 units in diameter. Its radius is 1 unit. So now we've got the numbers that have generated directly out of the geometric dimensions that we used. Now what I'm going to do is I'm going to do a simple little operation. I've used this to get me to the golden section, and now I'm going to just transfer that golden section from this diagonal over to this vertical line right here. Okay, So when I do that, you'll see right there. Now to do that with my compass point would be here. I'd open to this radius and I would just swing an arc over to here. And that gives me this point right there on my vertical axis. Once I have that point, I can now draw in this little circle right here. Again, this is not arbitrary. It's only once I've generated this distance right here. You can see this. Let's go back to, you can see what I did here. I'm getting this point like this. There it is. Now I'm going to abstract that, and I'm going to use this new point right here as a center. The radius of this new little circle is already defined for me. It's this difference right here. So I'm going to juxtapose the circle right there. All right. Just remember that circle because we're going to, that little circle, because we're going to come back to it. So now I really like symmetry, so I'm going to draw one on the other side. Well, as it turns out, and again, you can do the math on this, I've got a triangular here, a profile of a triangle here, and that just so happens to be the profile of Khufu's pyramid, which is interesting to me. And the numbers work out extremely close. You can calculate the slope to base length, and you'll discover that it's virtually 1.618. Now, if you used the exact ratio to lay out all your parameters for the pyramid, it would probably not be too, it would probably be indistinguishable from the one that is there. And is this a coincidence? I don't know. I suspect not, because I suspect that one of the legitimate functions of the Great Pyramid, if amongst others probably, was that it was a repository of geometry. And it really is, once you realize that the slope to base angle, the slope to the half base angle of the Great Pyramid is virtually the divine proportion, as we say, or the golden number, 1.618. So this is the geometry of it right here. And that works out to an angle of around 51.84 degrees, give or take a minute or two. Okay. You can approximate this angle very close by a couple of other geometric processes. I won't get into that today. It happens to be very close to the ratio of 7 to 5.5, for example, will give you very close to that angle. And there's a couple of other ways that you can get that angle. One is through the squaring of the circle exercise, which we won't have really time to go through. But so now we've got the profile of the Great Pyramid generated through this process of geometry. Let's put that little circle back in. Now here, this to me, when I discovered this back in the, I didn't discover it, I learned it back in the 70s through the work of John Michel. And I was quite flabbergasted by it. But here, let's see what I've just done now. Take the pyramid out. I've got my original inscribed circle in that square. And you all saw we went through the step-by-step process. You know how I got this small circle here directly through it. It's a direct derivation of the golden number. I keep calling it the golden number, the 1.618, okay? But let's keep going here. So here I've abstracted just those two circles. And now you can see that the relationship of those two circles is not arbitrary. It comes about as a result of a series of geometric operations, okay? Let's enlarge it here so we can get a better view of it. There we go. Same circles, generated same way, same ratio. Size doesn't matter. The ratio matters. Okay, so let's check this out. It turns out that that is very, very precisely the ratio of the diameter of the Earth to the diameter of the Moon. And you can do the numbers, and there will be slight variation because, first of all, well, we know that the Earth is not a perfect sphere. It's a spheroid. The moon is not a perfect sphere. So there are some deviations. Like I have here, the diameter of the Earth, 7,920 miles. Well, in actuality, the polar radius of the polar diameter of the Earth is the shorter of the two diameters. Shortest is polar diameter, longest is equatorial diameter. There's 26 miles difference. The vertical, the polar diameter would be about 7,900 miles. The equatorial diameter would be about 7,926 miles. But you'll notice, obviously, that if you travel from equator towards the North Pole or the South Pole, whoops, sorry, the radius of the Earth is going to be getting shorter, okay? The radius is going to continue to get shorter. And so obviously, as it's going from 7,900, I'm sorry, the diameter will be getting shorter. As you're going from 7,926 to 7,900, there will be a point at which you hit a diameter of 7,920 miles. Interestingly, that's almost precisely the latitude of the Great Pyramid. Just a little bit off, but it's very, very close. It's also very, very close to the area of a sphere that would have the same volume as the Earth. Now, again, the Earth is an oblate spheroid, right? Now, what would be the volume of a perfect sphere whose surface area was the same as the Earth actually is, but whose diameter was 7,920, and that would be, again, that would be the perfect sphere that would have the same volume as the Earth would be 7,920 miles in diameter. So you got a couple of interesting correlations there. When you take the combined radius of the Earth and the Moon, you end up with the Plato's sacred number, 5,040 miles. And he talks about that in the Republic and other places. Very interesting read. We don't have time to get into that. And there we juxtapose the Great Pyramid, height, and watch this now. So now notice what I'm doing here. I've got my original circle here, which is this red circle. That's the one we started with. That was the circle inscribed in the square. We now have the means to draw another circle, larger, and this one now is the vertical height of the pyramid. It's the 5,040 unit that you see right here. And we're going to use that as the radius, and we're going to draw another circle right here that will go from the center. Its radius is going to be from the center of the Earth to the center of this tangent moon, okay? It gives us this. All right. I'm going to put my square back in there. So I've got this square that now my original circle is inscribed within that square. I've got this new circle. And you'll see how it clips the square, the corners of the square. Well, it has been proven mathematically that you can't draw a circle and square, or you can't calculate an exact ratio. I mean, you can calculate that, but you can't really draw it mathematically, geometrically rather. And this is proven, like, for example, you can draw a perfect square, you can draw a perfect pentagon, right? You can draw a perfect hexagon. You can draw polygons that'll be perfect in their measurements and absolutely rational in terms of, internal proportions. If you take a square, let's take a square and make its side length 1 unit, its diagonal is then going to be the square root of 2. So you can go through this and you can calculate these things. But in any case, what happens here is we have sort of a solution to the classical, what's been called one of the 3 great treasures of geometry is the squaring of the circle exercise. And you cannot do it geometrically with absolute precision. You can approximate it pretty close. I mean, damn close, but you can't hit it exactly on. However, ancient builders knew several techniques for laying out a square and circle where the perimeter of the square is virtually equal to the circumference of the circle. So what we have here now is a very, very close approximation to a solution for the squaring of the circle exercise, because you could calculate the circumference of this outer circle, and you can calculate the circumference or the perimeter of the square. What's the perimeter of the square? Well, our original circle, if its radius was 1 unit, the perimeter of the square is 8 units, right? Now we could do the math on this, and we're going to find that it's slightly off, but it's darn close. Now, if you're using what I call the builder's triangle, which was, this is something we learned in Carpentry 101, the 3-4-5 triangle, and probably I'm sure some of you are very familiar with that. The 3-4-5 triangle is how you lay out and make sure that you've got squares or right angle corners, because 3, 4, 5, 3 squared is 9, 4 squared is 16, 16 plus 9 is 25, which is the square of 5. So what makes that valuable is that you've got the Pythagorean relationship laid out in integral values, in whole numbers. So we learned that like almost on day one in carpentry, using the 3-4-5 triangle, which is called the builder's triangle by some. I've always called it that, the builder's triangle. Now, if you use the builder's triangle in this, you discover something interesting, and I think we'll have time to go into it. But let's look here. This relationship, just get this image fixed in your mind, because here you've got a solution to the squaring of the circle exercise. You've got the Great Pyramid profile in there, and you've got now the Earth-Moon relationship to an really extraordinary degree of accuracy. You can do other things with it. You can put in a Seal of Solomon, which divides the circle into 6 equal parts. So here we've got approximation of the squaring of the circle through this operation of the sequence of steps that we just showed. Now watch this. Look at the center line of the sarsen stone circles out here and the blue stone circle. Whoops. So it turns out that the two most prominent circles in Stonehenge, concentric circles, virtually demonstrate the squaring of the circle exercise. Now, it's very possible, not proven by any means, it could be a coincidence, but given the accumulating evidence that ancient peoples actually were pretty aware and knowledgeable about fairly sophisticated geometry, I think it's a likely case that they did use geometry to lay out the template upon which the stones of Stonehenge were subsequently erected. But you can see right here, and you'll notice that when you'll notice the hexagon has the hexagram, the 6-pointed star has a hexagon inside. That almost defines the diameter of the inner bluestone horseshoe. In fact, if I was to use this basic geometry here and go lay out, if I knew my unit value, my module, if you will, I could go out there and I could lay this out on the ground using on a flat prepared site, using my center pole and a knotted rope. I could lay this whole thing out. I could duplicate this geometry. It would serve as a template. And if I brought in the same type of stones or the same size of stones, you could erect one that would be pretty much indistinguishable from what the original ground plan would be. Now, could it be an inch or a few inches off? Of course it could. But I think the point is that, as a builder, I know that there are tolerances we work through. Anybody who does machine work, any kind of measuring work, that there are tolerances in your technology and what you're working with. Now, I know that when we're doing the rough structural work on a building or a house, typically, we're doing excellent if we're doing 1/8 of an inch or better. We typically will try to actually work to a 1/16 of an inch. Might as well. the 16th of an inch unit increment is the smallest on our measuring tapes. But really, as far as like if the rough structure of a house, if you hit 1/8 of an inch of accuracy, you're doing good. Okay. Now, let's say we're doing trim work, finish carpentry. Well, now we're working to a 32nd of an inch. Okay, and it all depends on the application. You know, if we're doing fine furniture, we work to really close tolerances. So all of our machinery has to be very precise. You know, all our cutting tools and everything has to be very precise. Our joinery tools, all of that, to get the high precision. So it all depends on what your task is, what your goal is to determine the precision. Now, if I was going to, somebody said, hey, can you create a duplicate of Stonehenge out of whatever, concrete? Can you, if you said, well, can you quarry the stones, and transport the stones dozens of miles? And I'd say, well, that's probably a little bit beyond my pay grade at this point. Now, if you wanted me to, I could go out there and my team could build formwork and we could do cast in place concrete, and then we could, decorate it so it looked just like stones or whatever. But the point is that I'm getting at is by using this template here, it would be pretty much impossible to differentiate it from what the original may have been, because it's very, very close to this. But again, if we're talking about inches over from outside to outside of the sarsen stone circles is about 105.5 feet. Okay. So a half an inch or an inch over 105 feet isn't, it's not a game killer there. So that's the point there. So here, the interesting thing is, though, here I want you to take away from this is that we've got the same geometry unifying a number of different things here. We've got unifying the ground plan of Stonehenge with the profile of the vertical profile of the Great Pyramid, and even the Earth-Moon relationship. So there's numbers of different ways to play with this. I'm going to show you something else we can do that takes it like to the next level. So when you get the pyramid in, let's go back to the pyramid. Okay, so you'll notice there's this pyramid. Now I could have drawn the pyramid upside down, couldn't I have? I could flip this over and use the center of the moon down here, and I could have an upside down pyramid. Or I could flip it to the left using the center point of my moon here and drawing up, or I could flip it this way. So that's exactly what I'm going to do in this next image here, and you'll see it. Okay, you see what that is now? Now there's a couple of interesting things that's going on here. You'll notice that I've got the corners, the apexes of the pyramid are in the 4 lunar circles, which is what I'll call them. And then inside you've got this flattened octagon. Can you see it here? It's an 8-sided flattened type of octagon that's formed by the intersection of these, the lines representing this pyramid slopes. Okay? So I'm kind of creating some kind of little interesting geometry here. Well, watch this now. Here we go. See what I've done? So a couple of things what I've done here. I've taken the geometry that's yellow, I've extracted it, and I've rotated it so that we get this orientation. And the reason I've done that, I'll show you why, you'll see in a second why I've done that. This is, as it says here, should say here, this is the tip of a platinum needle. This is the, my God, I should have supposed to have a caption here. Let's see, maybe where did it go? Well, let's see here. Sorry about this. I got to get, here we go. Very sorry about this. Okay, that's it. A field ion microscopic image of the atomic lattice of a platinum crystal. I don't know why, when I went into presentation mode, it's truncating my slide for some reason. Oh, there we go. Okay, that's all I had to do. So there it is. It's a field ion microscopic image of the atomic lattice of a platinum crystal. Now, there's other geometric arrays that can be demonstrated. I'm just showing you this as an example that there seems to be hidden geometry on the microscopic level, but we also find it in other places. So keep this in mind as we go here. So now we've gone to this, and I'm showing how the moon is in there. And now I'm showing you this Newark. This is a earthwork structure that is up in Ohio. This is the ground plan of it. It's laid out to carefully track, if you know the vantage points throughout the course of the full cycle of a full lunar cycle, which it takes 18.6 years to complete, you can witness the moon in all of these different positions, rising positions on the horizon. So this was originally like a lunar observatory. And you see that the axis of the whole structure is the maximum northern moonrise. Now, there are apertures. These are raised embankments, and there are apertures through the sides where, if you're stationed at the auspicious vantage point, you can sight through the apertures. You can see minimum northern moon set, maximum northern moon set, minimum northern moon rise, and so on. And what each of these alignments is completed is defined during an 18.6 year cycle. Here's an artist rendering showing the alignment, the long alignment to this right here, the maximum northern moonrise. So every 18.6 years, the moon is rising on the horizon exactly where the axis of this structure intersects the horizon. Now that to me is extremely interesting. They obviously built this thing. I don't think it's an accident. I think that's silly to try to dismiss this as an accident. But the question then has to be is why did presumably Neolithic, maybe subsistence farmers or foragers or hunter-gatherers have any interest in building something on this monumental of a scale in order to track subtle motions of the moon that require a full 18.6 years to complete, when the vast majority of people today go about completely oblivious to the fact that the moon has this cycle. But whoever built this was almost obsessed with the fact that the moon had this cycle. And they laid out this tremendously large earthwork structure here in order to monumentalize that relationship between this site on the ground and the movements of the moon in the sky. And how interesting then that when we look at this, we find that same flattened octagon built into this structure. Now it's very, very precise. I mean, I can, let's say, believe, yeah, there it is. So there's the 18 acres of this flattened octagon here juxtaposed. And you can see it, the geometry is precise. I mean, it's within inches. So was this intentional? Did they know this geometry? I'm not going to assert that. I don't know. But the more we get into this realm, the more really extraordinary it gets because we begin to see these correlations and these patterns that we just didn't know were there. And our models of ancient peoples don't really allow for this level of mathematical sophistication, I believe. And if this isn't a coincidence, I mean, let's assume it is a coincidence. Well, it's a mighty interesting coincidence, if you ask me. If it's not a coincidence, then, then they must have known about this geometry, laid it out on the ground, and then moved hundreds of thousands of tons of earth in order to monumentalize this particular geometry on the ground and its relation to the passage and movements of the moon in the heavens. And it just so happens that this geometry also embodies this Earth-Moon relationship of 7,920 to 2,160. So there we have it. Most northerly moonrise. So here is the here's the geometric ratio. I mean the geometric alignment right to the center of the moon. So if you were, let's say, positioned on this point here, this mound, you could look through the opening in the embankment here, and you'd look right on to that position directly, rising on the northerly horizon, most northerly, once every 18.6 years. Now that to me is pretty damn extraordinary. And I don't know the explanation, but I think it's a question worth asking. Why were these people doing this? And really, how much did they actually know? So here, I'm just juxtaposing this back on the field ion microscopic image of a platinum needle there. Whoops. And there's a profile of the Great Pyramid in there. There's another system that I found to be very interesting, which is this. The traditions of Eastern yoga that talk about the 7 chakras. And I learned about this early on because I had the opportunity to study both with a Himalayan Swami and a Brahmin priest. And this idea of the chakras, which is really sort of, to me, got watered down with a lot of woo, but there's really a profound technology, inner technology, I believe, with this. And it's ultimately based upon vibrational frequencies. Those vibrational frequencies are related to the geometries of each of the chakras. And if you get into it, which I've done, you can, and we get into this in the classes and courses, we examine the geometries of each, the traditions go back thousands of years in the Vedic tradition, and we look at those geometries, we look at the angular relationships, the internal angular relationships, and the numbers describing those relationships, and discover that those numbers are actually numbers that can give us frequencies. So that's way beyond what we're going to be looking at here today. I have one more thing to show you, so I'm going to jump out of here for a moment. And I'm going to go to another PowerPoint show. And let's see if I can do this quickly. Yeah, here we go. Let me bring this over and see if we can pull this up. Well, let's see if this works. All right, I believe you're seeing this diagram of the Kuiper Belt and the Oort cloud. So this is, like I was telling Steve last night, we were looking at some of this. What we have here is the full structure of the solar system. Most people, when they think solar system, they think the planets from Mercury out to at least to Neptune, formerly with Pluto, define the outer limits of the solar system. But really, the planetary part of the solar system is only a minor part. We have these other 2 cometary reservoirs, the Kuiper disk and the Oort cloud. Here's another graphic by Ralph Myers, kind of shows the relationship. Way down here in the middle is the planetary sphere. Outside of it is this belt, this disk of comets rotating slowly around the sun, and then beyond that you have this sphere. This is my favorite graphic. This really kind of shows the architecture of the whole solar system, right? Now, what's particularly interesting about this is that we're at the point now, if you've learned anything about astrobiology, you know that, that there's a pretty solid idea now that life was essentially seeded on the Earth by the means of comets, that the hydrosphere was the result of cometary impacts delivering water to the terrasphere. So also, the precursors of life, the amino acids, the nucleotide templates, and so on, that we now know exist in comets. So it almost seems that comets have the very important dual function within the grand scheme of cosmic nature. One is that they deliver the fundamentals of the building blocks, the molecular building blocks of life to the Earth, and they deliver the water so that the appropriate matrix exists for those kinds of biological changes to occur. And however, I'm not arguing creation or just Darwinian evolution. I'm not getting into that. That's a very interesting discussion we have. I mean, there's even a theory called directed panspermia, which is that comets were the means by which the world was seeded with life as part of a deliberate exercise. Very interesting stuff to get into, and there's a place for that discussion. Not tonight, though. So I'm not getting into anything teleological here, although I don't exclude that. I'm keeping an open mind. But in any case, we've got this whole structure of the solar system here. Way down at the center, like the nucleus, we've got the planetary realm in which we inhabit. Now, in order to affect this whole process of delivery of biological precursors to Earth, we have to be able to get comets from these outer reservoirs that are vast on a huge scale, even to the point of tens of thousands of light years out to be into the Oort cloud. So we have to have a means of delivery. Let's keep in mind, though, also that comets I mentioned have this dual function. One, they may be fundamental for the inception of life on Earth. Also, they are also responsible for mass extinction events. It's still controversial whether the great impact at the end of the dinosaur era was comet or asteroid. As it turns out now, unlike conceptions, a few decades ago, there's no clear line of demarcation between comets and asteroids. In fact, a lot of what we think may be asteroids might be simply devolatilized comet nuclei. In any case, here's our problem. We want to get those comets from these reservoirs, and then I will mention this, that there are essentially two types of comets: long period and short period comets. The differentiation is based upon the geometry of their orbit. If they're elliptical, they're going to be short period because that means they're rotating around the sun. They're orbiting, not rotating. They're orbiting around the sun, usually in a sort of a cosmic ping pong game between Jupiter and the sun, as often as not. And that would be, they're elliptical. Then the dividing line between in the conic sections between a closed curve and an open curve is a parabola. So anything on one side of a parabola closed would be an ellipse, and then on the other side it's going to be hyperbolic. So if you look at the orbit of a comet, if it's elliptical, it's closed, and it's almost certainly originated in the Kuiper disk. If it's open, it's probably originated in the Oort cloud. If it's a hyperbolic, anywhere between a parabolic and to hyperbolic, it's going to, in other words, it's not repeating. It's coming in, making a perihelion passage around the sun, and then heading out to space, and will probably never return again. Where if it's a repeating comet, it's probably come from the Kuiper disk. Its orbit is going to be laying close to the plane of the ecliptic. Most of the objects that would be threatening near-Earth objects that would be threatening the Earth are in that plane of the ecliptic, right? Because if they're in the plane of the ecliptic, you can picture they're going to be crossing the Earth's orbital path repeatedly during their lifetimes. Whereas if it's a long-period comet on a hyperbolic orbit coming in, making one pass and going back out, there's a much more remote chance that there would be an impact, right? So most of the impacts are going to have been short period. They're going to be in elliptical orbits, and that can be asteroids, comets, or the overlap, whatever it is between the two. Okay, so now let's talk about something here. This was a study that was published back in, I think it was the early 2000s. I don't know, I don't have the date on here. I'm fastidious about remembering dates, but somehow I left it off. Anyways, a new study reveals that the locations of the four large outer planets, Jupiter, Saturn, Uranus, and Neptune, play a crucial role in shepherding comets into the inner solar system from a layer beyond the orbit of Pluto. From Neptune to Uranus to Jupiter, to Saturn to Jupiter, quote, comets are being handed off from planet to planet, says Harold F. Levison of the Boulder, Colorado office of the Southwest Research Institute. It's this celestial bucket brigade, he notes, that allows a select group of comets to grace the skies above Earth, flaunting their dusty tails as they deliver key organic compounds into our atmosphere. If this gang of four, Jupiter, Saturn, Uranus, and Neptune, were spread further apart, comets that rank as frequent flyers to the inner solar system, visiting at least once every 60 years, could never make the journey. If the outer planets were bunched closer together, the orbits of these comets would look radically different. This speculation, which may provide clues to the early lives of planets, stems from a computer model developed by Leveson and Martin J. Duncan of Queen's University in Kingston, Ontario. They reported their findings in June at a comet workshop at the University of Toronto's Canadian Institute for Theoretical Astrophysics. With the existence of the Kuiper Belt no longer in doubt, researchers have turned to another question. How do short-period comets leave this storehouse, and how do they venture into the inner solar system? A year ago, researchers provided the definitive answer to the first part of the riddle. In simplest terms, comets leave the belt because it has a slow leak. In 1995, Martin J. Duncan and Stuart M. Budd of Queen's University, along with Harold F. Leveson, reported the results of the most extensive computer simulation ever done of the Kuiper Belt. Two kinds of orbits, characterized by their relationships to the orbit of Neptune, place members of the inner part of the belt in a precarious position. Vulnerable to sudden chaotic changes in their motion, Kuiper Belt denizens in these orbits stand a reasonable chance over a 10 million year interval of leaving the reservoir they call home. Some of the Kuiper Belt escapees move away from the solar system. Others get flung inward toward Neptune. Once a comet falls into Neptune's gravitational clutches, the other large outer planets start to exert their own gravitational influence. In this way, some comets from the Kuiper Belt make their way toward the inner solar system, where they come alive in the sun's warmth. Yet the new calculations by Leveson and Duncan show that one shouldn't take such a model for granted. It's only because Neptune, Uranus, Saturn, and Jupiter are spaced exactly far enough apart that each has a chance of handing off a comet to the next. Aha. So it would appear that perhaps the spacing of those big outer planets is, dare I say it, not random. Well, okay, so what I want to do now to conclude, let's see if I've got it here, some images of, oh, well, I think I need to go back to my geometry show. So let's do that. I should be able to just put that down and go back to here. Let's see if I hopefully will have it here. Yes, we do. Okay. Very simple. Two simple squares. In a geometry class, lesson one is learning how to draw this right here. Very simple. It'll take you, just if you've had some training, it'll take you minutes. Even with mathematical zero, you'll still be able to do this probably within minutes. We start very simple. Now, what I'm going to do is I'm going to use these two juxtaposed squares and develop a geometry around this. Relatively a little bit sophisticated, but actually very simple. And you will see how each step is the result of the preceding step. So each step lays the groundwork for the next step. There's not going to be anything arbitrary, okay? We don't just start randomly putting points in this thing. You'll notice a couple of things here, that when you rotate one square on top of another by 45 degrees, the points or corners of that square will give you an octagon if you were to connect them. Okay, but let's go through a little exercise here. I have introduced what's called an octalpha inside. So an octalpha is an 8-pointed star. that you can draw without lifting. If you once you know how to do it, you can draw without lifting the pencil from the paper. So a pentalpha will be the same thing. You draw a pentagon, a five-pointed star, without lifting the pencil from the paper. This is an octalpha, and you can see it creates some interesting geometries here. We've got this eight-pointed star, right? And we also got an octagon. See, look, we got a perfect octagon in the middle there, an eight-pointed polygon, a regular eight-pointed polygon, right? So that was the second step. We start with this, we go to this. This should be familiar to you now. Here we juxtapose a circle. The diameter of this circle is going to be equal to both of the squares because the squares are exactly the same size. They're duplicates of each other. Okay, so we've established this circle. And now I'm going to do something similar I did in the previous exercise. But what I'm going to do is I'm just going to run projection lines on out from my octalpha, right? And I just run them out at random, and then I use my compass, my drawing compass, to establish the side length. Notice if you follow my cursor around, you'll see that it defines an octagon. You see that? So what we've done now is we've established four squares, peripheral squares, whose side lengths are the same as the side length, the edge length of my regular octagon. You see that? And all I need to do to create the square is I place my compass point at one of these two corners. I open to my requisite radius, and I just draw a couple of arcs. Voila, and it's easy to project this square. No big deal at all. Once you've done it, you'll be able to do it easily from that point on. But the reason I'm doing that is because I'm generating a whole nother set of circles that are going to, of course, be geometrically related to my original one, right? Now, my original one, is going to be my inscribed circle. And you can see how I've generated this. I had to create these squares whose side lengths are the same as the edge length of the octagon that was generated out of my first stage working of the diagram. And I'm just showing 8 of these spheres here, just to sort of, just for interest mainly. What I'm particularly interested in, though, is the 4 that are going to be in these squares that I drew. So we could calculate, I haven't done that calculation here for you, but you could easily calculate knowing the flat to flat distance on an octagon. It's a simple calculation to get the edge length of the octagon, and that would give you the side length of these squares. So now I'm going to do one more thing. I'm going to add this third circle. Now this third circle, you can see its radius is going to be the side length of the octagon larger than my first, I'll call it the orange circle. I've got the orange circle, the dash circle, and the red circle. The radius of the red circle is going to be the radius of the orange circle plus the diameter of the blue circle, which is the same as the edge length of the octagon. You got that straight in your head? Okay. So now I've actually created 4 circles. Now I've got my original orange, I've got my dash circle, I've got my blue circle, and now I've got my red circle. So the diameter, think of it, the diameter of the red circle is going to be the diameter of the orange circle plus the blue circle twice, okay? So let's just clean it up a little bit so we've got this relationship. Now you can see how we geometrically constructed all of the circles on here. And here is the math. It's no big deal. We're calling A to B first radius unit. That's 1, right? So I've got that up here. R, the radius, is equal to AB, and that's equal to 1. AC is the square root of 2. Well, how do we know that? Well, because we know that the relationship of any square, its diagonal to its side, is in the ratio of the square root of 2 to 1. So that's where we get this. If the radius is 1, then the distance from A to C is going to be the square root of 2, okay? We'll put that here. Then we've got BC, which is going to be the square root of 2 minus 1. So this little increment right here, BC, is going to be the square root of 2, which is AC, minus 1, which is AB. Can you see that? Okay, I hope you're following this. Also, you're going to see over here that CD is also going to be equal to the square root of 2 minus 1. Then we've got AD. This is going to be the radius of the large red circle, the all-encompassing red circle. And it's going to be AD is going to equal AC plus CD. Well, we've got those right over here. So we substitute those values in and we get the square root of 2 plus the square root of 2 minus 1. Simplifying, we just get doubling the square root of 2 minus 1. That is going to be the radius of my large red circle. Now, when we take AD and set it to the ratio of our original orange circle, large red circle AD to radius of the orange circle, original circle AB, we calculate that ratio and we discover it equals 1.83. Okay? 1.83. So now we're going to do something else. We're going to abstract those two circles, my original orange circle and my red circle, because those are the two circles out of this diagram that we're interested in. So now I'm flattening it out. We're looking at it obliquely. And let's see if there's anything whose ratios correspond. There we go. Sun to Saturn mean distance, 886.7 million miles. Sun to Jupiter mean distance, 483.7. Ratio of the Saturnian distance to the Jupiter distance, 1.83. So there, through a simple geometric exercise, we can create within a very, very precise margin of error. Now, of course, again, Saturn's orbit is somewhat elliptical. Jupiter's orbit is somewhat elliptical. They're very circular. You're also going to know that within that orbit, you're going to have a perihelion and an aphelion. So there's going to be some little bit of difference. Sometimes it's going to be outside the ratio. Sometimes it'll be inside the ratio. At other times within its orbit, it's going to hit that ratio dead on. Okay? We got to remember, when we're talking about this kind of system here, whether we want to call it mystical geometry, sacred geometry, Pythagorean geometry, Masonic geometry, they're all overlapped. They're all basically the same thing. Just like out on the building site, I know that between the ideal plan, the blueprints, the numbers on the blueprints, we're trying to transpose those with the highest precision and degree of accuracy possible onto the actual building site. So you've got these degrees or phases of transformation. It starts up here with a concept. This is how any architect or designer would work. Starts up here, or any science, really anybody who's creating anything, starts with a concept up here. In terms of us builders, it goes from here onto the blueprints, onto the paper, or now the digital. But now we have on there all the idealized numbers, all of the specifics down to a high degree of precision. Now we turn that blueprints over to the craftsman, and depending on their level of skill, they will duplicate the idealized pattern to a greater or lesser degree of accuracy in the actual manifested building, right? But you know what? Even the best craftsmen, if you come in there with a microscope, yeah, you're going to see that there's deviation, right? You can only work within a certain level, but each person who works in creative endeavor has to decide for themselves what are the degrees of tolerance that we must allow here for this. Okay, so if you're doing precision lens grinding, you're obviously working to much greater precision and degrees of tolerance than somebody building a house, obviously, right? But the point is that there's going to be a deviation of some small degree between the ideal and the actual. If I go look at a building and I'm trying to determine what were the original measures of this building, and I discovered that it's, let's say its side length is 36 feet 1/2 inch. I'm going to probably conclude from that the original intention was not to make it 36 feet 1/2 inch, but to make it 36 feet, right? And that would be a very safe assumption. So what I'm getting at here is that when we talk about the Great Pyramid, when we talk about Stonehenge, when we talk about the Jupiter-Saturn relationship, right, there will be a minor discrepancy. Is that minor discrepancy significant for the function of that particular geometric form or manifestation within the realm of creation? Maybe not, right? If we're talking about the difference between, let's say, the note A in an octave vibrating at 440 cycles per second or 432 cycles per second, how many people are going to hear that difference? Now, a very highly trained ear, I think, will detect that. You could say between 440, if you're slightly out of tune and you're, instead of 440, you've tuned your A to not to exactly 440, but let's say to 436 or 438, the average person is not going to detect that difference, see? So you got to keep all that in mind when you're looking at some of the critics of this. Oh, well, you're not exact. Well, okay, what do you even mean by exact? Because we're working within a high degree of precision here. The manifested system is very, very similar in all respects to the idealized system. Okay, so that is something to keep in mind when you're looking at all this. Now, in the courses that I do, we get into a whole lot of, first of all, we take it step by step through the whole procedure of how to go from simple to very complex. Then we look at applications, and there are some pretty extraordinary applications. Like I think what I just showed you is actually pretty significant. And when you remember that it's the geometry of the solar system that keeps this functioning through time, the delivery of cometary nuclei to the inner solar system. We see the geometry is inherent in the structure of the world that we inhabit, even on the cosmic sense. So I think at that point, we'll terminate there. I mean, we could go on. I've got many other examples, but I think we'll end it there. And I hope you've gotten some inspiration out of this and some ideas. And yes, thanks for joining us, and thanks for having me, Steve.
Well, thank you for being here. And does anyone have any questions out there? It looks like you got a lot of good comments.
What did you say? We have a lot of good comments?
Comments.
I got a laugh out of Stephen.
Here's a certainly guy. Gosh, I'm fortunate to be here at this moment. Thank you. Feels good seeking this knowledge of solitude and having this man confirm I'm on track and not too far behind.
Oh, good.
So people are getting a lot. I mean, competent statistic. And most important of all, thanks, bud. Love you.
Love you too.
So we have a pretty good audience here. And I know I picked up a lot tonight, and math is extremely important, whether it be geometry, trigonometry, or algebra or calculus. It's all interrelated. And I remember I never had trigonometry in high school. So when I get to college, I'm taking Calc 2 and it relies on trigonometry. So
well, you Steve, you're in college and you're taking calculus 2?
Yeah. Yeah, when I was in college.
But you skipped over trigonometry.
I had to teach it myself.
Ah, okay.
The problem is
you probably need to know a little trig for calculus 2.
But I looked. I had a friend. Some friends we had they had it. They were young kids, and you got to remember, I was in the Army for like 8 years before I went to college.
Okay.
So I had to relearn algebra, teach myself trigonometry, at the same time turn around and pick up calculus.
Mm-hmm.
I'm amazed I even got through that. But it grows on you. And I got a D- in Calc 2. But in Calc 3, I had a major comeback. I got an A.
Oh, way to go, man.
And then I had A's and B's the rest of my time. It just seems like when you work with this stuff, you develop like a maturity about you. And you
Yeah.
go back, you look at the old books and say, wow, how did I not get this? You know,
Well,
so
it's weird. A lot of times, and I've found this in the learning process, you might read something or study something that's very complex and you don't really get it. And then you kind of forget about it and it sort of marinates in your subconscious for a while, go a few months or something go by, and you come back to it and you go, oh, okay, I get it now. Um, I have found that to occur and continue to occur quite frequently.
and then again, it helps if you put the stuff underneath your pillow at night, sleep on it.
There
It
we go.
permeates your brain.
Well, maybe you could become the new pillow man, Steve. You
Uh,
could develop a series of pillows.
Here's another comment.
Have you?
Excellent work is always good, sir. Have you heard of the Medicine Hat Badlands Guardians geographic site? Tim Giant Face will be my prolific profile pic in California.
I've heard of it, and I had no idea there was 10 giant faces. Now that I'd like to know more about that. Who did that come from?
Uh,
Yeah, I'd like to learn more.
Crypto Alchemist.
Medicine Hat Badlands Guardians geoglyph sites. Yeah, being my profile visible. Hey man, oh yeah, Crypto Alchemist. I see that. Look at that. That's amazing. So I'd be interested. Do you think that's artificial, meaning man-made, natural, or I'll tell you, I'm inclined to think that it was both, that it was natural and then perhaps modified by humans. But of course, the question in my mind is the scale of this thing is so large. How do you do it without having the overview? And and this one that Crypto Alchemist is showing is the only one that I was aware of. I had no idea there were 10 more of them. That's an area I really would like to explore because at the end of the last ice age, this was a very interesting terrain. It was the site of these tremendously catastrophic, large terminal ice age floods. And in my mind, okay, so these must have been post floods, but well, because obviously these floods completely rearranged the landscape. But I've been very interested in the question between the giant geoglyph, which is the profile, and the geological events that occurred there. Let's see. What are your thoughts on ancient alchemy, monoatomic elements, Ormus? Oh my God. Whew. Okay. Yeah, I do have some thoughts, but I don't know if I could really get into that too much right now. I'm not going to claim expertise. You know, I've read a number of works and have known some people who've been involved with it over the years. I have not personally experimented with Ormus, so I don't know. I cannot speak from that perspective. Um, I have looked quite a bit into alchemy, and I think that there's a lot going on there in terms of the relationship between particularly exotic metals as the kind that are delivered via comets and asteroids, particularly the platinum group metals and the philosopher's stone. Also, the overlap between alchemical traditions and the Grail, the stories of the Grail, because I think clearly alchemy is at the core of the whole Grail mythology. Let's see, quick thoughts on radiant energy. Yes. Quartz, which would then be, yeah. Okay, see, now this is where I was kind of alluding to this with the idea of, the musical notes and the frequencies, the vibrational frequencies, which we find, like, for example, think about the Vedic time cycles, the yugas. They're built upon a structure of four yugas that starts at 432, I'll say 432 cycles per second. I mean, in terms of the Yuga, the great cycle of ages, it's 432,000 years. And that is the Kali Yuga. And then you have the next age is the Dwapara Yuga, which is double the length of the Kali. So it's 864,000. Then the next one is three times the Kali, which is the Treta Yuga, which was 1,296,000 years. And then the next one is the Satya Yuga, which is 4,320,000. So what you've got there is an octave sequence. You've got 432, which is the vibrational frequency of the note A. I think it's the Phrygian scale it's called, and several others. And then you have the octave, which is 864. Then the next octave, which is 1,296, and then the next octave, which is 1,728 cycles per second. Then all of those together gives you a higher frequency octave, which is the Maha Yuga, the Great Yuga that encompasses all of the others, and it's 4,320,000 cycles per second. So my quick thoughts on radiant energy is that, yes, I would think that geometry is the key, resonance is the key, because we know that things that are in harmonic relationships can resonate with one another. I think there's a lot of really interesting research that could be done along those lines by using resonant frequencies and deriving those frequencies from the numbers of geometric relationships.
And then how can I contact you to set up an interview together? I can share all my research discovered with you, and I'm sure there's probably a couple people who'd want to do that.
Well, yeah, I guess Randall at randallcarlson.com.
So anyway, one more. It's nice to see certain devastation.
Had they been hard. Well, now Sirius, how does that fit into the equation, which is interesting in itself? It's likely that Sirius B went nova sometime in the recent astronomical past, and when it did, it likely had effects or consequences for our own solar system. Like, in fact, it may have even induced instabilities in the sun. Yes, one of the terms I use to try to describe the scale of what our thinking needs to evolve to is cosmic ecology. We have to realize that our planet Earth is not an isolated system. Now, up to this point, it was assumed that the open side of the system was the sun, and because the sun's variability was considered to be almost non-existent, this is why the term the solar constant. If the solar constant is so constant that its variability can be discounted, then of course we don't even need to include it in our thinking about global change. It's all going to be internal to the system. I don't think that's accurate or true, and I think we're already realizing that the Earth, in the example that I gave tonight, with the idea of the architecture of the solar system, and it's how conducive it happens to be, just coincidentally, for affecting these processes, these astrobiological processes, if you will. So it seems to me that we need to be thinking about a larger framework, and I call it we're part of a cosmic ecosystem, and we have to think of an ecosystem literally in cosmic terms. And so, yeah, if somebody has really interesting research, now I have to say, I have been overwhelmed with stuff in the last 6 months to a year. So if I don't respond immediately, please cut me a little slack there. Because I'm doing 2 podcasts, and I got my day job and
Sure.
some other stuff going on. But I'm very much interested in communicating. I would like to find out more about those 10 geoglyphs. That's very interesting, because that area of the North American continent to me is a very interesting area because of what happened there during the end of the last ice age, and the geomorphic work that was done there is incredible. So what is the connection between the geoglyphs and the reshaping of the landscape that took place during the Great Meltdown?
Okay, so where can they find your podcast, Squaring the Circle?
I think just Squaring the Circle. Mike, it's hosted on HowTube and Rumble.
Okay.
Now, I've not gotten, you're only, I think, up to 14 episodes, so it's relatively new. My other podcast, which I haven't been doing regularly, that's why I started the second one, is Cosmographia. Now, there's 109 episodes. Now, if you're interested in the geological and astronomical and architectural aspects of this, you'll find a lot of stuff there. And I'm there with my pal and colleague Brad Young, uh, the uh, the Allen brothers, Russ and Kyle, who do their own podcast called Brothers of the Serpent. Um, and it's the four of us. We have other guests sometimes, but it's mostly the four of us. And we have a good old time, but we talk about a lot of the kind of stuff we've just been talking about. But we're really heavy on the geological, archaeological, astronomical aspects of these topics. So you'll find 109 episodes under Cosmographia. Cosmographia is spelled with a K, like in the Greek, original Greek, and the new one is Squaring the Circle. Let's see here. If I just put in Squaring the Circle, let's see what comes up. If I put in Squaring the Circle, Randall Carlson, hit the search button, and there we go. It comes right up to the YouTube videos. Episode 1, Squaring the Circle. Yeah, there we go. I did it just by putting in Squaring the Circle, Randall Carlson.
Okay. Well, with that, I think we need to bring this to an end tonight.
I'm with you.
And thank you for being our guest and everything. Maybe next year you consider maybe coming to our conference.
I would. I talked about this with Mike, and it was just I was too squeezed with things before and after to do it this year. If I'd planned ahead of time, no, I would have. Yeah, I would like to cut because there's a lot. I'm sure there's a lot of stuff there I would be interested in and want to learn more about.
Yeah, I learn something every time I learn something every day, from these people that come to the conference.
Yeah, I'm sure you do. Look at there.
Anyway, so with that, I'm going to go ahead and bring up Mike.
Yeah, and Mike.
If he's here.
Yeah, maybe bring up Mike, and then I can say goodbye and good night to Mike.
Yeah, I don't know if he's.
They're actually friends.
Oh, there he is.
Go ahead. Hey. Friends. How are you, Randall?
Hello, Mike.
Oh, sorry. Go ahead.
Well, I was asking Mike if he was listening in.
I was listening to every word. I had a question. I feel like it's going to, send you off on maybe a half-hour rant, so I'm hesitant to ask.
Cut out of here.
I know. But at some point, I want you to explain to this audience, like, for example, the question that came to mind when I heard you tonight, first of all, it was mind-blowing stuff. I mean, just the relationship between geometry seems to be ubiquitous.
Yeah.
I mean, based on what you presented here, it's everywhere. And I just wanted to ask you, what does that mean in relation to all categories of scientific study? Is it?
Well, since I'm an expert in all categories of scientific study, no, geez, I don't think I could answer that question in less than a couple.
No, yeah. But is it true or not true that geometry, or perhaps sacred geometry, I'm not sure which term you like best, it's everywhere. I mean, it seems to be everywhere. Isn't that what you presented tonight?
Yeah, pretty much. Yeah, pretty much.
All right.
Right. I even showed you, the geometry of my middle finger. Now, I'm not going to isolate my middle finger, Mike, because you might take it wrong. But yeah, I showed you the geometry of my middle finger. So you didn't know, probably, I'm sure that Steve didn't know this, that was the origin of that sign. Was, look, my sacred geometry is, my golden section is better than your golden section, so stick it. No, that's not true, Steve. I made that up just on the spur of the moment.
That's great.
All right. Well, I'm gonna take my leave here. Yeah. So
So we're gonna real quick before you go, we're gonna show these guys, the audience, real quick, how to access the TeslaTech live stream. So, are you gonna be joining online and maybe visiting the chat room, saying hello in there? Or
if I don't get squeezed between two different road trips, I will. Yes. If I don't, Good. It's because, like I said, my window in there, it's bookended with road trips on both sides that I have to be prepared for. But probably, I mean, I would love to. I would love to join in. make a few comments here and there.
Great.
But yeah, I mean, I'm definitely going to be listening into as much as possible and getting. I'm sure, Mike, I can arrange with you to get this. So the whole thing, all 5 days is going to be recorded, right?
Yes.
All 5
Yes.
days.
Yes.
And so for one price, you get all of that.
Correct. Correct.
Wow, that's a pretty good deal, Mike.
So the 5 days will all be live, and you can come and go as you want. But if you buy the live stream, to access that live event for the 5 days, you get a recording. You get
the whole thing.
The whole thing. Yeah,
and
which you can keep for yourself, download, and enjoy in perpetuity.
In perpetuity. You've got, so you can listen to it all at your leisure.
Correct.
That's a hell of a deal.
Okay,
but you have to buy the live stream first.
Yeah, of course, the live stream. Do the live stream. But even if you can't do it, if you're up on climbing Mount Everest or something, you can't do it. Buy it anyway, and then you'll have it.
Yeah, you'll get the best bang for your buck if you buy the live stream at $99 and then keep the recording. That'll be the best dollar value.
Now, is that included in the personal attendance? Do you get a copy of the recording if you buy a ticket to sit in the seat?
No.
No. Okay.
No, in person, you have to either buy DVDs, or I would encourage everyone to go ahead and sign up for the live stream. Even if you're coming, because that way you have it. You want to buy the DVDs.
That makes sense. Sure, that makes sense.
And I want to encourage everyone not to forget to give us a thumbs up. If you enjoyed tonight's show, and that helps us, let's everyone know that we have a good show here. So, and if you click on the QR there, the QR will take you to the live stream. And this will help benefit the Randall Carlson organization.
And I appreciate that very much, Steve.
If you use this QR thing, $99, you can't beat that with a stick. Normally we charge $300 for the DVDs. It looks like Mike dropped out. So.
Okay. Yeah, he was looking pretty blurry there, and I don't know. So let me see.
It's kind of weird because on the thumbnails it was real clear. Then you get him up there, you're clear, I'm clear, but he was real blurry.
He was. Okay, now how do I get out of here? Do I go to?
If you go to the bottom, it says Leave Studio.
Yeah, that's what I thought. I don't see it.
We got the chat, but anyway, I'm just going to say it to everyone. Don't forget to come to the conference, or at least get the live stream. My phone number is there. We still have rooms to fill. We have plenty of rooms still in the main area. And your biggest problem will be getting enough sleep at night, because we go practically 24 hours, it seems.
Wow.
So if you get a chance, come on down. And with that, I'm going to call it good night. And thank you, Randall, for being here. And thank the audience for coming.
All right.
And you all have a great night.
Good night, all.